Okay, let's take a look at solving some real-world confidence interval problems. There's one thing I have to show you before we go forward with that. Let me rewrite the formula that we've been working with. We have the confidence interval is going to be given by the sample mean plus or minus the z-score times a standard error, which we have looking like this. Oops. All right. There's one problem with this formula, and the problem is right here. We don't have the true population standard deviation. If we had a true population standard deviation, chances are we'd have a true population mean, and we wouldn't need to go through all this effort to estimate what that mean might be. So in real-world cases, what we have to do is we have to change this whole standard error term just a little bit. What we're going to do is we're going to estimate this population standard deviation using the sample standard deviation, which of course we can calculate. So instead of having CI being plus or minus Z times, we're going to put an S here for our sample standard deviation, and then we're going to divide not by n, but by n minus 1. We have to adjust the denominator of the standard error equation to take into account the fact that we're only estimating the standard deviation of the population using the standard deviation of the sample, and that we don't actually have the true population standard deviation. Okay, with that said, let's tackle our first problem. Let's imagine that we're conducting a study of the wage structure at an industrial plant that employs several thousand computer assembly technicians. We want to get a rough idea of the mean hourly wage of this population of technicians, and we're going to randomly select 129 personnel files and record the hourly wages that we see in those files. In the sample, we're going to find a sample mean of $8 per hour. And we're going to find a standard deviation. We're going to calculate this again from the data itself of $1.70. And we should note again that n here equals 129. Okay, so the first thing that we want to do is let's compute that standard error. Remember, our standard error is going to be equal to the standard deviation from our sample divided by the square root of the sample size, n minus 1. In this case, that's going to be equal to $1.70 divided by 129 minus 1, the square root of that, and that's going to come out to about 15 cents. So we have the first part of what we need for the confidence interval. Again, the confidence interval formula is given by CI. I'm not going to use an equal because it's not an arithmetic operation here. Our X bar, $8, plus or minus a Z value times our standard error, which we've just calculated at 15 cents. Okay, what's that Z value going to be then? Well, we're interested in the 95% confidence interval, and typically I'll be asking you questions about the 95% confidence interval. I may sometimes throw you the 90%, sometimes the 80%, perhaps the 99%. But if you go to the Z table and you need to look up the value for a tail value of 0.25. Why 0.25 for the 95% confidence interval? Because remember that we are looking for this 95% area of certainty. So we have 5% left over, but each tail has 2.5 or half of that 5%. So what we're going to do is we're going to look up the Z value for a tail of 2.5. All right? And that's always going to be the same thing. That does not change. That's 1.96. Down here it's negative 1.96, and up here it is positive 1.96. 1.96. All right. So 1.96 times 15 cents is going to be equal to 29 cents. So our confidence interval is going to be bound on the lower side by $8 minus 29 cents, which equals $7.71. And on the high side, it's going to be equal to $8 plus 29 cents, or $8.29. The thing to remember here is that a different sample will yield, obviously, a different mean and a different confidence interval. What we're saying with these confidence intervals is that in 95% of all the intervals that we could construct, depending on what our sample was, we're saying that 95% of all these intervals will contain the true population mean.